Swayam Prabha. Digital India. Educated India.
So that's why I just wrote minus x squared. So let's do this problem. Let's take a potential minus half kx square. I'm writing it like a inverted oscillator. This is called an inverted oscillator. So let me see whether these things make sense to you. Half m dx by dt whole square is a kinetic energy. Okay. This is the potential energy. So this is the total energy. Okay. I'm going to call that to be equal to 0. That is this total energy here. I'm taking it to be 0. So the potential energy and the kinetic energy and potential energy are related like this for an orbit which is going to start from somewhere and go till that point. All right. So now how do you solve this differential equation? So we can just cancel half on both sides. You'll have dx by dt equals some square root of k by m into x. Okay. So now integral dx by x square root of k by m into t. Now what is this t and what are the limits I need to put? I want to start from some point, let me just call that a, and I want to go till 0. So I'm going to start from some a which is some negative number. Let's say minus a to 0. Okay, a is some positive number. Minus a to 0 or actually I can, it doesn't matter. Let's say 0 to a to 0. It doesn't matter. So that you don't get confused on this. So this is the time it takes to go from a to 0. So what is this integral? Log x. Log x, goes to infinity at x equal to 0. Okay, actually it goes to minus infinity. Yeah, it goes to minus infinity. So you have to look at all the, you have to look at the time, you have to look at these integrals, the sign of these integrals properly. So you do all that. But it's primarily coming because such an integral diverges. In fact, it is coming, so that is the mathematical reason for that. Okay, so, but, yeah.
If I'm not wrong, I can see that in the graph that you have drawn, the state space that graph.
Yeah.
It's trying to turn into an ellipse. It's starting from cylinder and then slowly turning into an ellipse. What is theta doing, like to make it into an ellipse?
No. Let me. It's not turning into an ellipse. It's an ellipse. These are not ellipses, and this is not an ellipse. You can easily figure out what that curve is. It's not an ellipse. Okay.
What is this ellipse?
Oh, because this total energy, So you write down the total energy that's equal to that. So twice mgl equals the total energy, which is half mv square plus the kinetic energy. I'm sorry, potential energy. 1 minus cos theta. This is the equation of that. So now you can take this mgl on this side and you can find out what that curve is. Exercise. Okay, so that's the single pendulum. We haven't yet come to the double. That's why I needed 2 hours. Okay, so, I've told you that things are predictable. Now I'm going to tell you that that's a lie. Huh? Quantum.
I mean, quantum has applications in classical.
No. Don't see. Quantum is something different. Don't. Quantum is something like, you're at the moment for you. At the moment for you, quantum should not be of any concern, at least in this lecture. I am not telling you that I'm lying because of quantum. I'm well within classical mechanics. Okay? Because if you look around you, common sense tells you that this is not correct. Nothing is predictable. Not even the weather. Right? So, in fact, the most elementary thing, like I take a coin and I toss the coin, nobody knows whether it's going to come head or tail. You can do any amount of mechanics and do several PhDs, but you're not going to be able to predict whether it's head or tail. Huh?
Sir, what if you have a special coin with heads on both sides?
Okay, look, I know that you guys are kids, so I'm going to leave that, okay? So, but. Huh? What? No, but why cannot you predict a coin toss? Don't tell me quantum mechanics. Yes? Yes, please.
Sir, because if you were to predict the exact path that the coin would take and land on, you would have to look at interactions of the air molecules and the coin, which is too complex to be predicted.
Okay.
But Laplace is given, sir.
Yeah, but maybe the demon has too much knowledge. Yeah.
Sir, I would say because so my understanding is because a small change in sorting conditions can lead to a vast change in the final result of your the final consequence of your statement. So it becomes really hard to understand.
Why? And why is it that this is true for the coin toss, but not for the when they are sending a rocket to the moon? And they're sending a rocket to the moon, they know where they are going and what they are doing. Yeah.
Isn't that like for our single pendulum here, we were able to find equations and then integrate them. Such an equation is impossible. Like that integral.
Oh, why? No. Mechanics problem in a rigid body, a coin is not a very complicated thing at all.
But to get the equation and then to solve it. Like,
Equation is Newton's laws, nothing more different.
Our equation here, we use that integral. Is it possible that that integral doesn't exist for our common situation?
Integral doesn't exist doesn't mean that integral doesn't exist means what? We may not be able to calculate the integral, you and I, but it will exist. Somebody can calculate it or the computer can calculate it.
But that's only two step. That's only via measurement. We can't.
Yeah, I mean, there are so many things which we cannot work out by hand, but nevertheless,
Sir, is it
Yeah.
like what Pranav said? Is it that the coin is more dependent on the initial conditions than the rocket?
than the rocket.
Than the rocket.
Uh,
Like the question you asked, the reason why the rocket isn't as affected by all of these pseudo random variables is because it doesn't.
what do you mean pseudo random variables? Where are the pseudo random variables?
It's not the random.
Which way? Which one?
Okay.
Like, are you referring to what he was saying? The air molecules and so on.
Yeah, if you were to consider how air resistance affects the coin.
So you're talking about air resistance. So then my question to you will be, if you toss the coin in a vacuum, will you be able to predict it? Yeah?
Yeah.
Who told you? Huh? Yeah, but the question is why? Because after all, this is mechanics. You guys told me about all this.
Sir,
Yeah.
I think it boils down to the way you toss a coin. The coin is more dependent on your action of tossing it.
You can have a machine. There are also things called pinball machines. There are machines, if you're worried about your and their actions, You can have machines which are giving you the same kind of initial conditions. You still will not be able to predict. Yeah.
Because coming to that rocket and coin analogy, as Pranav said, a small change in initial conditions widely changes the output. For a rocket, that doesn't happen because we keep using our using the control mechanisms on the rocket. We keep it from diverging to an unpredictable
Control, you're saying.
Get it back to the
Yeah, but has anybody done that for a coin? Control coin, and I'm sure that the BCCI would have invested a lot of money if there is such a thing.
magnetic dice and stuff.
There are ways to flip a coin where it just lands on one side.
Make the other side
Spin it,
heavier.
instead of flipping it, spin it like that.
No. Why are you guys thinking? Oh, I'm talking about a normal coin, and you can always cook up a coin like you said, both are heads. That's not solving the problem or asking the question. Yeah.
Just an idea. Is it that there are just two equally likely things and it's just by chance that one of them is taken?
Yeah, very good. But what is chance? So this is precisely the question I'm asking. Does mechanics allow for chance? Because we are saying probability. Probability is another thing in mathematics. They'll tell you if you toss the coin, probability half, you'll get head. Why probability? When you have Newton's laws, why do you need probability? Why do you need chance? What is the origin of chance? Because a state is known. Then we know the past and the future. So the evolution of complexity is good that you guys have all these things, but actually I've come a bit late, so I have to ask the organizers or anybody here how long I can keep on doing this.
As long as you need to.
Are you sure? I mean, is there another speaker, ma'am? At 4 o'clock or something? Is there somebody else coming? Okay, I can carry on.
We can take some.
Okay, thanks.
Sir, since he said pseudo random, wait.
Look, I want to eliminate.
Sir, that made me think that maybe everything is predictable, but some things are just not understandable enough for us to predict. Hence, we call it chance.
Sir, or is it
Good question, yeah.
Or is it just that you can predict everything only up until a point in time, and once you cross that time, anything which follows even Newton's laws can become unpredictable at that time?
But why? And what is that time? So it's a good. So these are all very good questions. I mean, very good responses, and they're all coming closer to the truth. Yeah.
We cannot which are called with common mechanics. We cannot find the final state without stepping through some number of intermediate states, because we can say that it might diverge at some point, and we don't know where. So that's what I meant in the sense that we can't. Is it like not possible to find final state given just the initial condition of when you toss the coin, final state when it lands, without stepping through all those states.
Sir, an additional question, sir.
Wait, let me hear from the other side. I'm not hearing. Yeah.
So, like he said, the difference between the rocket and the coin is that with the rocket you're controlling all the conditions initially, finally, and during the journey. So you know its state at every single point in time. But when you're flipping the coin, it's impossible to know its exact velocity and position at every single state of time.
No, but you don't need to know at every single point of time. You just need to know at any one time. When you're tossing, right, you need to know that it's flat. You need to know that it's tail on top, right? And that it is horizontal. That will tell you position. And then velocity. You're going to give it some velocity.
So I have a question.
Yeah.
So even under vacuum conditions, projectile motion is still like, for example, projectile motion is still completely predictable.
What is projectile motion?
Okay. Yeah, okay, two body.
No. Projectile motion is what when you throw up something on a gravitation, it's coming.
Gravitational field.
Yeah.
Acceleration constant.
Yeah,
One direction.
yes, sir. So if you were to
No, even three directions and all that is predictable. Yeah.
But if we have
But-
two bodies and
But for some reason, when you toss a coin, it becomes unpredictable.
Exactly. I'm asking why. Because a projectile, that means a point particle you can predict, right? When you are giving it some shape, you're saying you can't predict or that it looks unpredictable.
So is it because of rotation?
Of course, it is. If you don't give it any angular momentum at all, angular momentum, it will just go up and come down. Then it is predictable. Okay, but it is going to rotate like this, and then it's going to come and land. Of course, he also mentioned that is it like, or somebody mentioned that is it like there are two possibilities, and both of them are, like for instance, is it? By the way, you do this integral carefully, okay? You can take a to b, and then you can take b tending towards 0. That will be a better way of doing that.
About these chances,
How about?
you said that we can't predict the coin because two people like these chances that are and it's kind of random which one actually comes out. But then in something as big as a rocket trajectory, where are those chances? Why aren't we considering like there could also be a chance that slightly divergent?
It will. By the way, it has nothing to do with size. Let me tell you that these things have nothing to do with size. You can have large objects which are also very unpredictable, as the coin toss is. Our own weather system is like that. It's a very large phenomenon. Okay. I'm not even talking about biology and so on, where also physics is the underlying thing, chemistry. There are many things which we cannot seem to predict. And I have bought one of these things here. So maybe we will concentrate on this for the time being, okay, rather than even going to coin tosses. But what is happening to this? So let me come to this. This is a double pendulum. So a double pendulum is two pendulums, okay, and there are two angles now. There is this theta 1 and theta 2, the angle from the vertical of these two pendulums. There are two angles which you need to describe the position of the double pendulum. Is that clear? That is, you can hold this theta 1 fixed and you can move this like this, or you can hold this fixed and you can move this like this, okay? So there's a very important difference between this and the pendulum which we have discussed so far. This has got 2 degrees of freedom. Theta 1 and theta 2 are 2 degrees of freedom. And the state is now given by these angles theta 1 and theta 2, as well as their velocities theta 1 dot, or the velocity theta 1 dot means the derivative of theta 1 with respect to time, theta 2 dot. So now you see it's a 4 dimensions. We can't imagine 4-dimensional space. So already the state space of the double pendulum is not something which we usually imagine on a day-to-day basis. But that's it. There is nothing else in this. There is only this gravitational force which is acting on both of them. Okay? There's nothing else.
Can we say the same thing for the molecule? It has an x, b, theta, and omega, and since it's 4 dimensions, we can't visualize or we can't physically understand it. Hence, we can't predict.
No, nothing like that. Okay, just because, see, human beings are only a small part of the universe. Because we cannot visualize a 4-dimensional phase space doesn't mean that it becomes something which is unpredictable or anything like that. Not at all.
So that's that follows along the argument that I gave, because it is, we call it predictable because it is unpredictable because it's unpredictable to us. But in reality, maybe everything is not random, everything is pattern oriented or something. And since we can't understand it, we call it chance.
So, yeah, so this is all fine, very good. What I'm trying to get at is the following. at the beginning I was talking about the clockwork universe, the picture of the Laplace domain. Everything is predictable if you're given a state, and also not only predictable, that things are moving in periodic orbits, moving in cycles, okay, and forever repeating the same pattern over and over again. So that is one aspect. And then we have this aspect of chance, which we are seeing in real life. And I'm trying to say that what one of the things which I want to tell you is that this is not incompatible. That you have simple laws of motion, namely mechanics, and mechanics, the laws of motion are the same whether it's 2 degrees of freedom, 100 degrees of freedom, or 1 degree of freedom. Newton's laws are the same throughout, except that you need to write down 4 equations now instead of 2 equations there. For each of these quantities, there will be 1 equation, or there will be 2 second order equations. There are forces for this as well as this. This pendulum is affecting this pendulum. Okay, these 2 pendulums are interacting with each other. Now, is this sufficient to make the motion look chaotic, or is this something which can become chaotic? Of course, now there is a lot of things, and you might have already come across this as an example of chaos. But what is chaos, and what are the conditions for chaos? So that is one thing which that I want to just mention in this. So, but first of all, the major difference is that there are 2 degrees of freedom, and this 2 degrees of freedom means that you are in a higher dimensional state space. Okay, but otherwise, equations of motion are still Newton's laws. You can write them down. It's slightly more complicated. By the way, has there been a lecture by a colleague of mine on Lagrangians and all that? Well, one of my colleagues said he will talk to you guys about that. Okay, so his name is Titas. So Titas will probably tell you how to look at Lagrangians in a very simple way, and then you can use that Lagrangian to find out these equations of motion. Okay. Now, suppose the teacher who scolded you when you did large angle was given a double pendulum, and you were also given a double pendulum. What would you do? No, you would start. That teacher is important. You would start with small angles. Now, what happens for small angles in a double pendulum? Works the same way means what?
So small angles for which state?
Both.
Both together.
Yes. That's what a small angle means. Otherwise, you'll get a scolding.
It would probably be a little period rather than being totally
No. Okay, ladies and gentlemen, please don't think that everything is unpredictable or chaotic. Okay, that's not the message I want to give here at all. Okay, the case when this theta 1 and theta 2 are small, in fact, you can make them again these kind of approximations. Sine theta is theta approximations, and it will look like 2 harmonic oscillators which are coupled. And coupled harmonic oscillators are a model of solids and so on. Okay, but that's it. There's a simple oscillation here, and each one of them will have a frequency. Okay, each one of them will have some frequency, omega 1, and there will be 2 frequencies. Okay, so there will be effectively 2 frequencies. Let us say they are not the frequencies of the individual pendulums because they are actually coupled. So you have to do some kind of trick there and get 2 frequencies instead of 1 frequency. And the resultant motion of this double pendulum will look like, approximately, for small angles, it will look like some kind of combinations some A plus B cos omega t. You guys have come across this kind of? Is it unpredictable or chaotic or anything? What sort of phenomena give rise this kind of thing?
When you have two harmonic motions adding on to each other.
Yes. So what kind of it's not just one. It's not just a simple sinusoidal thing. It can give rise to beats and various other things, depending on this ratio omega 1 and omega 2. Okay. So this is how it looks, and these are called normal modes. Okay, and there are two normal modes, and if you put it in that particular normal mode, the motion will be periodic. Okay, so let me try to put it in one of the normal modes here. Okay, this is, let's say, small angle. This is approximately a normal mode. There's nothing chaotic here. It's, as somebody said, almost like a single pendulum, right? It's just moving back and forth. So this is in sync, or both of them are moving. Like this small pendulum, when it is on the left, that thing is also on the left, etc. Now let me do the other one, the other mode like this. Okay, this is already some kind of superposition like that. Okay, so let me try again. It's almost periodic. Okay, it's just that not exactly periodic, because this itself is not periodic. When will this not be periodic? Yeah, sit down. When will this not be periodic? No, when omega 1 by omega 2 is irrational, this will not be periodic. Okay, prove it. You can see that. Okay, when it is rational, it will be periodic. So typically this will be something which is not periodic. But now you see, all the real fun on this, even for the single pendulum, is when you have large oscillations.
How do you interpret an irrational frequency? I don't get.
Ratio of the frequencies is irrational.
So, but can you divide two rational numbers to get an irrational?
Huh?
One of the frequencies has to be
The ratio has to be irrational.
So you cannot divide two rational numbers to get an irrational number.
Yes.
So
one
once,
of them has to be.
yeah.
Yes.
So how do you interpret an irrational?
You don't believe in irrational numbers or what? Interpret means what? Why do you need an interpretation of square root of 2?
Also, it actually create in reality of something with an irrational frequency.
In reality, isn't like large.
Long back there was a guy called Pythagoras. He is supposed to have committed suicide because he realized that there are irrational numbers. I hope you guys are not like that. There are irrational numbers. This is a reality. Okay. What do you mean whether you can? Of course, there are irrational numbers. If you don't believe in irrational numbers, what numbers are you going to believe in? Because 100% of the numbers are irrational. Then if you don't believe in 100% of the numbers, you take the numbers between 0 and 1. Okay. 100% of the numbers are irrational. 0% of the numbers are rational. Okay. But that's another lecture.
Sorry, you blow our mind in 2 ways at a time, sir.
What?
Oh.
Sir,
What?
is this about countable and uncountable?
Exactly, yeah. There is an uncountable infinity of irrational numbers, countable infinity of rational numbers. Yes. No. Ask them, they will count it for you. Okay, guys, we are getting out of mechanics. 1 by 1, 1 by 2, 3 by 1, 2 by 3. I have written on the board a scheme for finding all rational numbers between 0 and 1. Huh? I'm taking all the denominators 1, 2, less than that, 3, 1, 2, 4, 1, 3 numbers which are. You will eventually get any rational number in this list. Slice them in the
Every
middle.
diagonal number you can add what you want.
Yeah, you can always, in the middle, you can always get a mean.
Yes, you can. Of course, you can get any number between them. But what I'm saying is that you can order all rational numbers like this, and therefore it forms a countable set. So there are as many rational numbers as integers. You can make a one-to-one mapping between this and 1, this and 2, this and 3. So if you thought that there were more rational numbers than integers, you're wrong. They are exactly the same number. Now you may believe me that 100% of the numbers are irrational. It doesn't mean that there are no rational numbers. But anyway, irrational numbers are very much part of whether you can measure an irrational, whether you can prove that some length is rational or not. If you can prove that something is rational, you can prove something irrational. If you tell me that this length here is exactly 1, and you tell me that this length is exactly 1, you know that that length is square root of 2. I don't know why you're doubting that.
My interpretation of that has always been it's impossible to create exactly one.
Mathematics tells you that it is possible. All right, now let's come back to the double pendulum. So now, you see, these are the interesting points, the unstable equilibrium points. Okay, here the large pendulum is an unstable equilibrium point. So this is already unstable. It is going to be driving the small one into also an unstable. So this will be actually, by the way, the maximum energy I can give it without giving any kinetic energy, right? So maybe we will go crazy and start from this initial condition and see what happens. Shall we?
Yes.
All right, watch. So follow the small guy, and you thought that everything was dead and it was moving, and then it wasn't. It suddenly started again. The point is, try to predict the small pendulum. I'll start again from the same initial condition. Okay, top. And tell me whether these two things are the same. Now it's become it's losing energy. Actually, I had a slightly better pendulum which was lost by some students, and so they kindly made me another one, but this is not that great. So I'm starting again. Okay. Now I want you to keep comparing. Remember the previous pendulum motion and do this. This seems, see, I thought it was dead, but it's not. So there is a transfer of energy between the 2 degrees of freedom. Now it's come down to one of these things. If I give it even more energy, right? Let me try to become a bit more crazy and give it a lot of kinetic energy. So one thing which we notice is that in none of these cases the motion is periodic, or this kind of a thing is called quasi-periodic. The double pendulum, when you give it large energy, and it need not be that large, okay, it can be something like this. The double pendulum is an example of a nonlinear system, okay. So nonlinear is an important word. Nonlinear. The restoring forces are nonlinear functions. Like I wrote here, cos theta is a nonlinear function. Nonlinear means just not linear, that's all. The only linear function is like a theta in one dimension. So a harmonic oscillator restoring force, Hooke's law, is a linear force law. Actual gravitation, the pendulum, is nonlinear. And when you have 2 degrees of freedom and you have nonlinearity, this leads to these kind of unpredictable, what looks like unpredictable motion, what looks random actually. It's not random, of course, in the sense that it's governed by definite equations of motion. And if one knows, in principle, one knows the initial conditions to infinite precision, you can predict what is going to happen later for all time. But the catch is, just as this rational irrational discussion, when you make a measurement, you can never say that something is exactly starting from this initial condition. So instead of starting from, let's say, 0.1, you could have started from 0.100001. That is sufficient. So errors, if you start from some error delta x at time 0, and if that error is growing in time in this manner, e to the power of lambda times t, it's a power of something like this. This is called an exponential growth. This is the error at a time t. Then this is very bad. Very bad meaning that errors will just proliferate very fast and you won't be able to predict. So for example, if you have something which is growing like this, 2 to the power of time t, delta x0. Okay, let us say that this delta x0 is 10 power minus 6. You have initially measured something to 1 in a million. After what time t will this be of the order of 1, which means like 1. 2 to the power of t is growing. 2 to the power of t into 10 power minus 6 is equal to 1. 2 to the power of t is 10 power 6. T is approximately how much? 20, because 2 to the power of 10 is 1024. So 2 to the power of 20 is approximately 1000 times 1000, which is million. So 20 is not a very long time. It will become that. You won't be able to tell whether it started, and these can be completely different. Okay, so in fact, these systems which are chaotic are considered to be systems in which there is such a growth. And these things are called Lyapunov exponents. So there is predictability. However, for practical purposes, it's not predictable beyond a certain time. In fact, somebody mentioned that. I think you said that you can predict for some time and then not. That time is given by this 1 over lambda. In fact, people started appreciating this only when computers came into play around the 1960s. And then they were trying to do some weather models. And they were integrating the equations. You know, everything is well known. Fluid equations, everything is well known. And then they found that it is not possible to predict beyond 5 days. So this lambda was such that it's 1 over 5 days. And so that was the excuse that was given for why they are so bad at predicting short-term weather. The weather system itself is given by nonlinear equations, which are called Navier-Stokes equations, which are the fluid flow equations. And errors are natural because you can't measure all the initial conditions of the atmosphere exactly. And therefore it leads to this. The coin toss, which I gave you, is also a similar example. Although it is much less complicated than the weather system. And there are interesting models of coin tosses which can be understood by you with basic mechanics. I would advise you, if you want, you can Google Keller separate article, Mahadevan, who is from IIT Madras, mechanical engineering. There are these articles by them on coin toss itself, if you're interested in looking at the coin toss as a problem. Yeah.
So why do nonlinear functions necessarily mean that these errors are going to grow exponentially?
Doesn't. It is not a necessary condition. I'm sorry, it's not a sufficient condition. It's necessary. Okay? That means that you can have nonlinearities, and doesn't mean that there is chaos always. Okay? But you can't have linear systems and be chaotic.
So then what are the sufficient conditions for chaos?
Sufficient conditions for chaos, one can't really, okay, there is some things which I can tell you, and that is one of the things is this 2 degrees of freedom. Okay? Sorry? Yeah.
Does true chaos actually exist in this space? That's not what I mean. But then generally, sir, like, at the end of the day, can we actually get something that's truly, can we actually produce something that's truly chaotic?
What do you mean? So, but it's a good question. Look. Okay, what do you mean by truly chaotic? This is a complicated question. It goes back to philosophy. Okay? Because what do you mean by truly chaotic?
Cannot predict it in any way possible. So, for example, at a coin flip, we can at least predict that 50%. When it tends to infinity, 50% tends to 50%.
Yeah, but you can't predict the next coin
Can't
toss.
predict the next coin flip.
Yes.
But then there's things that we cannot even predict to that 50%.
Like what?
That I'm not aware of. But then,
No, but then why are you talking about something which you have no example of?
because sir, I've heard of something where they said that true chaos does not exist. We cannot simulate true chaos. At the end,
No, but what do you mean by chaos? Well, you have to understand that. What do you mean by understanding? See, a coin toss is something where if it's completely random, right? So why I said it's a philosophical question is it comes to what is randomness. What is randomness is another thing which you can talk a lot about. Okay, what is randomness? For example, suppose I give you square root of 5. You guys can find out what is square root of 5 on your calculator. You have a calculator by any chance? Do people still use things like square root of 5? Okay, so it's some irrational number. We know that, right? You can tell me already what it is. 2 point. Look, it doesn't matter to me. Okay, what I want to say is 2, 3, 1, 0, 1, 2. I'm just writing some random numbers out of my head. Whether it's really chaotic or not, she has to tell. Okay, but let me tell you some other mind-blowing things about irrational numbers like square root of 5. Square root of 5 contains all these numbers here. Would you call that random? Would you call it truly chaotic or random?
Sir, in one way you can say it's truly chaotic, but another way you cannot say it's truly chaotic. Because at the end it's an irrational number, so maybe the algorithm accomplished somewhere there inside that.
Of course, yeah. I mean, it has to be a digit between 0 and 9. It has to be one of these 10 digits. Okay. So let me tell you that if you take this, any irrational number, okay, I have to qualify that, but let's say any irrational number, almost all irrational numbers, you take like this and you find out how many ones it has or how many zeros it has. How many you think? Okay, how many fraction? What fraction of numbers will be 0? 1/10 will be 0. 1/10 will be 1. 1/10 will be 9, etc. Okay? How many numbers, what fraction of 2-digit numbers will be 31? Huh?
1 by 90.
1 by 100. No, 1 by 90, yeah, 1 by 90, yeah.
Why 1 by 90?
Sir, because there are only 92 digits.
0, 1, 0.
Hey, then how many zeros are there?
No.
Asking fraction.
Yeah, the fraction. Fraction of 2-digit numbers. How many 2-digit numbers? Why 90?
1, 2, 3, 4, 5, 6, 7, 8, 9. That is it.
No. 0, 1, 0, 2, like that. After all, yes, 1 by 100. Okay. So, in fact, irrational numbers are like this, that you can find exactly that for any number. So, you can take any sequence like this and you can find exactly 1 by 10,000 of them to be like that. Okay. And not only that, if you ask how many times is this random number 3101 coming in this irrational number, you will find that it comes infinity of times. It has to come because you're saying that it's actually 1 in 10,000 times it's coming there. So what I'm saying is that this irrational number seems to have all kinds of complexity in its digits. In fact, you can do this and you can have some random number generator like this. You are asking a computer a random number, it's giving you something. Why do you believe that? Yeah, it's got an algorithm, but it's giving you a random number and you are actually then basing a lot of things on those random numbers. Okay? So then that's what I'm saying as to what is a random number. After all, a computer is also using some algorithm. But hold on. So now let me tell you that the square root of 5 is not so random. Why? What pattern?
There's no pattern, but we can always
Calculate what?
certain we are arriving.
We can be sure of certain conditions being satisfied.
Anything unpredictable has a predictable or finite probability or a fraction.
No. Can you guys give me a simple formula for square root of 5 which doesn't have all this complexity in it?
How do you calculate? No, but
2, 1, 5.
Huh?
Right? 1, 5.
no, but you
And measuring it
See, you
upfront,
can
measuring it exact to infinite precision is how we do that, which is
can manually calculate root 5.
No. All that is. So, do you guys know this formula? So, let me write down the formula. Do you guys know this number? Hey guys, do you know what this number is? Golden ratio. Golden ratio is simply related to square root of 5. Do you know an expression for the golden ratio? Huh? Actually 1 plus, I guess, because this is 1 plus that. So 1 plus. Continued fraction. Yeah. Sorry?
I think root 5 or root 2 or anything of that sort would become like 1 plus 1 by 5 plus 1 by.
There is a continued fraction like that. Even square root of 2 has a representation which is very simple. But pi does not. E does not. So this is called a continued fraction.
What we differentiate between arbitrary and integer numbers.
Yeah, there are these distinctions, but what I want to emphasize is that you can get square root of 5 by a very simple algorithm which does not involve any randomness. The continued fraction expansion of this is very simple. It is just one repeated. So it doesn't look random at all. So from one perspective, it doesn't look random. From another perspective, it looks random. Now look, I don't want you guys to get confused a whole lot. Okay? Yeah. Is random.
Okay, you see that because it's divide and see, you're not leaving it up to chance that there are lots of percentages.
Oh yeah, you're absolutely right.
Then how can you call it random?
So you give me out of your head, okay, a set of random numbers. Give me.
9, 7, 5, 2,
Tell me.
4, 3.
Okay, we'll stop. You can go on like that. I am telling you that this number is there in square root of 5. Somewhere.
Sir, I think
So the random number which came out of your head is there in square root of 5. That way it is random. Okay? That way it looks random. Yes?
so it's all about finding patterns. Then if you want to define true chaos and
Not exactly finding patterns. Yeah. What is chaos is a very good question. No, you did not ask that. You said is there something with true chaos? Huh.
Something related to like observations. Because even if you are calculating each number one by one, say of square root of 5, then depending on when you observe the next number, if someone has already seen that number, for them it's not random. But for someone who has seen the number, who has not seen the number, it is truly random.
No, but you see this, what I was telling you. That in that sense it is random. Any random string of numbers you give, it's there. It's there. In that sense it's random. Okay, look, let us move on. Okay, we can go on for huh? What is chaos is very good. Huh? Yeah, okay. Definition of chaos. Okay guys, pipe down. So, but before that, you see, you guys ask me too many questions, so then it becomes a random walk.
So there are two primary questions. What is chaos and what are the sufficient necessities for chaos? Those two questions are all. Hey, no, that's not correct.
Blame her. Okay. Pipe down, guys, pipe down. Pipe down, pipe down. By the way, is there some water anywhere?
So we have water. So we'll give.
So are we differentiating between chaotic and random?
Okay, look, I need to address two things at this point. Conditions for chaos and what is chaos. Okay?
Yes, sir.
So let us concentrate on that. Conditions for chaos. Okay? Now I said first of all 2 degrees of freedom is important and not 1. Why is that? Why is 1 degree of freedom not sufficient for chaos? No, I wasn't asking a question. I was, because there's already too much of feedback. So it's because there is one constant of motion. So there is one constant of motion. Let's take 1 degree of freedom. 1 degree of freedom, there is one constant of motion. What is that constant?
You don't know what the constant will be.
No, you know.
It's a length of the pen, it's a point.
No, not length. No, okay.
Direction, like hours.
No, the direction is not constant.
Minus plus.
Time is not constant.
Initial.
No, look. What do you mean by constant of the motion? Constant of the motion does not mean things like mass, length, which are the parameters in the thing. Okay?
Give me a constant.
Not a constraint. A constant of motion is a function of the state which does not change with time. It's a function of position and velocity. If you take this at some time, let's say 0, it should be the same value of the function at a later time. This f you will then say is a constant of the motion. Okay? Now tell me, for 1 degree of freedom systems, what is a constant of the motion? Direction of what?
Y-axis. The y-axis.
See, think simple pendulum. Okay?
Energy.
Energy, ladies and gentlemen, energy. Total energy. Huh? Because kinetic energy is changing, potential energy is changing. The sum of these two is not changing. It will depend on the initial condition. It's not like every state has the same energy. Obviously not. If you come back to the picture which I have erased here of this thing here, this has energy of 0. This has some energy, maybe 1, 2. This has energy 2 mgl. Okay? Each one of them has energy. So as time is flowing by, there is only energy which is constant here.
So, but we have to assume that all forces acting are completely conservative.
Conservative forces, Hamiltonian conservative. There's no friction. Okay? Total energy is constant. Now, even if suppose it's not conservative, as long as there is a constant of motion like this, then there cannot be chaos because of what I mentioned here. There's only 1 degree of freedom, which means like there is a position and a velocity associated with it. And the motion on this phase space, x and p, or x and velocity space, is some curve like this. Okay? And because there is one constant of motion, some f of this is constant, you can solve for x in terms of velocity given this constant. This is describing for you a curve. Okay? And it cannot intersect itself because of this one state is giving rise to this. So it cannot do some crazy thing like this. It cannot do because it's intersecting itself. Okay? So 1 degree of freedom systems with one constant of motion can never be chaotic. Now let us come to 2 degrees of freedom, like this double pendulum. What are the constants of motion? But before that, I will ask you something maybe slightly hard, but it is it's already. Huh. Okay. Let's take a particle which is now moving inside a circular boundary. Think of a carom board, but a circular carom board. Okay. And what happens when the particle goes there? It will get reflected, and then it will get reflected, etc. I didn't draw it very well, but it's like light rays going inside, bouncing off. Okay. Now let's assume elastic collisions, so no energy loss. There is a particle, you are given it some velocity, it hits the boundary, gets reflected, keeps getting reflected. What are the constants of motion? Very good. Total energy is still a constant. Okay. But first of all, even before that, let me ask you how many degrees of freedom? How many degrees of freedom? 2. So this already has 2 degrees of freedom like this double pendulum. Why 2? Because I need to give you 2 positions. Let's say r and theta or something, okay, or x and y. Need to give you 2 positions. So there are 2 degrees of freedom for this. Total energy is still a constant because there's no friction. Any other constant? Radius of what? That's not a constant of the motion. Okay. The constant of motion, as I said, here it should be a function of the state. The mass of the particle, these color of the particle, these are not constants. That is essentially energy. Energy is just half mv square. It's not an independent constant. Of course, you take energy, square it. It does not give you another constant. Yeah. Very good. This angle actually does not change. This angle does not change. And you know, this is related to a classical mechanics quantity. This looks like a geometric one. What is the classical mechanics quantity? Angular momentum. Angular momentum. R cross velocity. I don't know whether you guys have done angular momentum. Angular momentum is a constant and it's related to this theta being constant. So actually there are 2 independent constants of motion. They are independent because you can have the same energy and different theta. Same theta, different energy. Yeah. What is?
This situation you described here,
Yeah.
are we saying that like a state space or whatever situation?
This is not the state space. This is the real space.
So he's asking for a supposed system of angle where angular momentum is important.
Yeah.
Would this be considered the state space for that system?
Yes, yes. So you can consider you can consider just the velocity and angle. You can still consider just the velocity and angle, or or just the position. Angular momentum will be just r cross velocity. Okay, so it doesn't matter what things. But you can consider there are different combinations of things you can consider. But basically, position and velocity. You don't have to complicate life. Okay, but here importantly, there are 2 degrees of freedom and there are 2 independent constants. One is energy and 2 is angular momentum. How do you think you can break energy? Let's say we don't want to break. Okay, how can you break the constancy of angular momentum and place what instead of circle? If you place nothing, it will just angular momentum will still be conserved actually. Because there's no torque on the thing. Okay, replace circle by what?
Oh, any rough shape.
Any shape. Why rough?
Rough in the sense that you can't any at the point the derivative doesn't exist. So
No, why all that?
there's no incident, there's no angle itself.
No, okay. You're going to an extreme case, okay? Ellipse. Okay. Ellipse is a good suggestion. Hey, you guys like to clap a lot. Okay, look. Look, ellipse is a good example. It's a harder example. Energy is still conserved, of course. Okay, there's no friction. Angular momentum is harder here, but there is another conserved quantity which is, slightly above. You have to work a little bit harder. But you do know that for ellipse also there is. How do you describe an ellipse, by the way?
Distance from
A constant. Okay, so if you have a particle which is going through one of these foci, it will go through the other foci. This leads to a second constant of motion, and it's the product of the angular momentum about the 2 foci. It is the product of the angular momentum about the two foci. This angle is no more a constant, but it is still got two constants of motion. So give me some other shape. Hyperbola, something close curve. Ah, too complicated.
Should it be a regular shape?
Not necessary, but I don't want you to think irregular, like he's saying some fractal, all kinds of things. But actually, let me tell you.
Any irregular model.
Let me.
Regular shape.
No, no, no. Actually, I wish I had my presentation. But let me tell you that another simple shape is a simple shape is a rectangle or a square. Okay, hold on. Here, what are the conserved quantities? Energy. Second, that's it.
Because if we hit that exactly at the corner.
Corner, yeah, corner is problematic. Let's ignore corner. Angular momentum is not conserved. Yeah. So what are there other conserved quantities? There is, okay, and it's rather simple to see what that conserved quantity is. What is the kinetic energy here? What is the total energy, by the way? Half m, velocity x direction, velocity y direction. This is the total energy. Okay. Now let's say that it is going and hitting here. It's coming back. What is happening to Vx and Vy?
So we I see we say Vy is
Vy is opposite. So what is happening here? So now can you tell me the second constant of motion?
Vx square plus Vy square is 1.
That is, I've already written. That is one. What is the second? Huh? Yeah?
Vx times Vy.
No. Yeah? This is kinetic energy. Because there's no potential energy. We have not put any forces. Okay.
So one second.
Think, yeah. Huh? No.
Some of the moduli of
Very good. Sum of
modulus of the speeds, that is.
speeds of each of them. Very good. So actually Vx square is a constant, Vy square is a constant. The sum of them is a constant.
So when it yeah, isn't that the same thing as the energy?
The energy is the sum of these two. These two are independent. Vx square, Vy square are two constants, or you can consider this as one and this as second.
Sir, in that case, then if we have those two independent constants, can we not say that the total energy is just a result of the constants here?
Yes? You can.
So our two constants here are Vx square and Vy.
Yes?
Not the energy.
No. There are three constants. They are not all independent. One is the sum of 2 and 3. They are not independent.
Here we are talking about only independent.
Huh?
One is
One.
like derived, right?
We were talking about only
2 and 3 are the only real things. One is like
It is your this thing. You can say that 3 is 1 minus 2. It doesn't matter. You have two independent constants of motion.
that's what.
Okay. Now this is now coming to the crux of the matter. If you have something like this, for example, circle here. Okay, I have put a circle here, and I have put semicircles here, and I have put straight lines here. It looks like what? It looks like a race track. Huh? It's called a stadium billiard. A stadium billiard This has only total energy as conserved. It does not conserve angular momentum, it does not conserve any other thing. Okay? This is an example of a fully chaotic system. It is just free particles. It is just moving in here. If you do this, you will get something which looks like that. Unfortunately, I haven't got the simulations, but you can always see this. If you start from a bunch of initial conditions which are very close by velocities, after a few bounces, they will be all over the place. So here is an example of that. Another example, simple examples. These are all studied, proven examples. Take a square, you remove a circle from this. So now a particle is bouncing like this. This is called a Sinai billiard. Also fully chaotic. Now you see, even actually simple shapes like triangles are very hard. Only equilateral triangle you can actually see what is happening. You take an isosceles triangle and then you try to see what are the orbits inside. It's not exactly chaotic, but it is not simple either. It's not periodic, it's not simple. So the conditions for chaos is that the number of constants of motion should be less than number of degrees of freedom. So this double pendulum, total energy is conserved. Well, not in this real pendulum, but let's assume that we are ignoring friction. Only total energy is conserved. There are 2 degrees of freedom, only total energy is conserved, and it is nonlinear, and therefore it's capable of showing chaos. It does not mean that every orbit in this is chaotic. Low energy orbits are not. High energy orbits are chaotic. Okay? Now, if you look at where physics started with the solar system and the earth and so on, right? What is the shape of Earth's orbit around the sun? Huh? Elliptic. Do you know how to prove that? How many constants of motion are there for the Earth? Huh? Actually, now how many degrees of freedom is there for the Earth? Let's assume that the sun is fixed. Okay, how many degrees of freedom for the Earth? 3. It's in space somewhere. Okay, there are 3 degrees of freedom for the Earth. You're ignoring all the internal shapes and you're ignoring you and me. Okay, otherwise we are having a lot of degrees of freedom. Now, how many constants of motion? Total energy, angular momentum. Very good. So energy, so let's say that there are 3 degrees of freedom. Okay, total energy E. Angular momentum, which angular momentum? There are 3 components of angular momentum. Remember, R cross momentum. It's a cross product, it's a vector. K hat. Oh, you mean along the... But what about the other? Actually, how do we know, that angular momentum is conserved here and not conserved here? It's very simple actually. Angular momentum is conserved here and not here because this has a circular symmetry. Circular symmetry. This doesn't have a circular symmetry. This doesn't have a circular symmetry. Here also there's no circular symmetry. Angular momentum relies on circular symmetry of the potential energy. Okay? If the potential energy has symmetry, that results in constants of motion. Now, the Kepler's laws, the gravitational law has a force which is going as 1 by r squared, right? It's a gmm by r squared, and the potential is gmm by r minus gmm by r. R is the distance from the sun, let us say. This has a symmetry of rotation. It only depends on the distance. It does not depend on which angle it is placed in. This results in angular momentum being conserved. And in fact, it results in all angular momentum being conserved. So these are called central forces, which you will study. And there are three angular momentums components. It looks like there are too many constants of motion, energy, but you have to check whether these things are actually independent or not, because you don't know, there may be some relationship between them. But actually for the Kepler problem and for this two-body problem, things are even more interesting. It turns out that only for a force like this, or potential minus gmm by r, there are additional constant of motion. And those are additional constants of motion are called Lenz's vector. Now, whatever it is, the number of degrees of freedom. No, I can't describe a Lenz's vector now. But I'll just tell you that there is one more vector. But this is an important point which I want to make. That the number of degrees of freedom is, let's say, 3 in this case. The phase space is how big? There are 3 velocities and 3 positions. So 6-dimensional state space of phase space. Okay? And you cannot have more than 5 independent constants of motion. You cannot have arbitrarily large number because there are too many, each one constrains the motion. Cannot have more than 5. It turns out that for this 3-degree of freedom system, because of the existence of this Lenz's vector, there are actually exactly 5 constants of motion, and that's why independent, and that's why we are moving in a closed orbit at all. Otherwise, why should you move in a closed orbit? We are in 3-dimensional space. So in fact, if the force law was different, let's say 2.5, instead of this Lenz's vector will not be conserved, and it turns out that we will not be necessarily moving in a closed orbit. So this is what I'm saying is these are things which are called super integrable. By the way, this full thing is a Runge Lenz's vector. If that helps you, okay?
No, sir, it doesn't, sir.
Huh?
It doesn't help us.
Okay, look, it doesn't matter. I'm just telling you that there's an additional constant of motion in this case. But here comes the interesting question. Why only sun and earth? Why are you guys not taking into account the moon? It's not that far away. Why are you not taking into account Jupiter? No. Black hole is far away. No, she likes exotic physics, clearly. Black holes and quantum mechanics. So, it's not bad. I mean, you're right. No. Okay. Question really. How do you know things are going to move in an ellipse? What? So actually, let me tell you guys that the whole study of chaos started with this problem, which was posed by some king. Yes. Oh yeah. You guys know. I believe it's a Netflix serial or something. So the 3-body problem. The 3-body problem, as it's called in physics at least, is the 3 gravitational objects, not just the sun and the earth, but say sun, earth and moon, or sun, earth and Jupiter, or actually, well, the solar system has got many more objects, right? Now what happens? The number of degrees of freedom goes up. The number of constants does not go up. And the 3-body problem can show chaos, and does show chaos. So the first problem in which people studied this carefully, by people I mean actually Poincaré, is the gravitational 3-body problem, and the problem was the following: is the solar system stable or not? Well, you seem to know now, but it was an open problem with a lot of money. The stability of the solar system problem, just as the instability of the pendulum or of the double pendulum, is the solar system chaotic? For example, Pluto was for a long time a planet. It was demoted from a planet. It has got a positive Lyapunov exponent and is known to be chaotic and will leave the solar system after 1,000,000 years.
Your guess, are we at the unstable? Is the Earth an unstable equilibrium of this?
No. Earth is not in an unstable equilibrium point, and also you cannot say that you can't talk only about the Earth. You have to talk about the entire solar system. Like in this pendulum, you can't talk only about one pendulum. You have to talk about both the pendulums together.
Yeah, which is the universe. Yes, sir.
That is unstable. Thanks. Okay, guys, wait. We have only addressed one part of the problem.
What is chaos?
Yes, we haven't come to that.
What is chaos?
Also, how you have to have time for every
You lecture us tomorrow also. Possible to lecture us tomorrow also.
I said only 2 hours. You guys are. Okay, hold on, guys. What was the question? What is chaos? You have time tomorrow or what?
Yes, sir.
What is your free time tomorrow?
You don't know, but there will be times, sir.
You don't know the schedule? Because there are very simple models which you can explore to find out what is chaos. Okay? So let me write down a very simple. All these things are slightly hard. 3-body problem and all is hard for me. Okay? But let me write down something which high school children can do. You guys are high school children.
Logistical mapping.
Yeah, he knows. Logistic map. Okay, look, this is an iterative map. If you give me x0, r is some constant, okay, you will find x1 like this, and then you will find x2 like this. Iterate. You can write a simple program, right? You guys can, you know Python and so on. Now, this logistic map as a function of r will show very interesting behavior. It's fully chaotic if r is equal to 4. Wait, hold on. And this x0 you take to be less than or equal to 1.
Sir, isn't R dependent on different conditions? Like if you're programming for a population of bacteria, R will vary.
Forget about bacteria and all that. So this is just a map. So R is a parameter. Yeah, there will be complex bifurcations as R is changing from 0 to 4. Okay, it's a complex set of bifurcations. But let me just tell you very briefly what is chaos. Okay, and then we will leave. What is chaos? 1. Sensitive dependence on initial conditions.
Also comes down to strong sensitive.
Somebody can be more sensitive than others. Hold on. Sensitive dependence on initial conditions is defined like what I defined in this delta x thing. Okay? Exponentially sensitive. You can define that as sensitive dependence on initial. 2. It has to have a sensitive dependence on initial conditions. 2. It should be what is called, let us call it some name and then I'll tell you what it means. Ergodic. What does ergodic mean? It means that, let's say that here you have some state space. Okay? And you start from some point in the state space. It will be ergodic if it comes arbitrarily close to every other point. Okay, suppose this is the point, it will wander and it will come here close to this somewhere. It will be called ergodic if it is like that. Arbitrarily close. So it's up to you. You say it has to come within 10 power minus 10. If you wait long enough, it will come.
Sir, right, then I can tell every single function is ergodic because
Not function. This is actually dynamics. Huh? So this is state space. So this is an initial condition, and it could be a double pendulum or anything like that. Huh?
but then I can still define it by telling my arbitrary constant is 473.
No. So obviously you have to take something small, right? I mean, if you say that it has to come arbitrarily close to this, not arbitrarily far. That is arbitrarily far.
Sir, what's a non-ergodic state space look like?
Non-ergodic will be something like this. You have a state space. So you start from here, maybe it will just move here. If you start from here, it may move just here. Okay? Yeah. So in fact, these billiards which I showed you, if you they are not ergodic. If they have sufficient constants of motion, it's not ergodic. Which one? No, only the chaotic ones are ergodic.
Respect to the entire board.
Yeah, so actually by this state space, I mean also velocity space. It should include also velocity space. State space, remember?
Velocity has state.
So it's not necessary, it's not the position alone.
Velocity has state itself. Yeah, so when you have state space, why do you need velocity space?
By the way, since you guys are talking about velocity space, let me ask you one question. You said that the motion of the Earth around the Sun were ellipses, right? That's in real space. What is it in velocity space? What do you mean? There is Vx and Vy. Velocity space. What is Vx and in Vx and Vy? This is a question for you to think about. Oh, you have extra mirror. No. You see. Yeah. So you guys have something now. Okay. So we are forced to stop at this point. So if you guys have some time, please you can tell the organizers. I will write to the organizers to arrange. Tomorrow or next week also I'm there. So you can. Is it? I was not prepared. They dragged me out. Thanks a lot. Hey, thanks a lot. Thanks. You know, I really enjoyed it. Huh? Abreya, thanks. Project, huh? You guys are all set? You have taken projects? The thing is, I'm not around after June. I'm not around in June. You'll be doing a project in June, right? Oh.
Those days are like presenting a project.
If you guys are still free, you can approach me.
It's not yet allotted.
It's not yet allotted.
Please,
If you are not allotted, you can. Oh. I'm in physics department. Hey guys, I am in Humanities and Sciences block 215. My email is Arul.
Can we email you asking for?
Yes, you can email me.
Thank you, sir.
Swayam Prabha. Digital India. Educated India.